What if the next big battery didn't look like a battery at all? Imagine giant blocks quietly rising and falling inside a towering structure, not to build anything but to power everything. No wire sizzling, no chemicals degrading, just pure motion. It might sound like something out of a sci-fi novel, but it's already happening, and in one of the last places you'd expect. While the world races to solve its energy crisis with lithium, one country is lifting an entirely different solution into the sky. There's a force we've known since childhood that's suddenly rewriting the rules of how we store power. But how does it work? And why is it spreading so fast, especially in the world's biggest energy market? Let's pull back the curtain on a game-changing technology rising, literally, above the competition. Lifting energy to new heights. Gravity batteries are emerging as a powerful and sustainable solution for large-scale energy storage, utilizing one of the most fundamental natural forces, gravity. These systems function by lifting massive weights using surplus electricity, typically generated from renewable sources like wind and solar. When energy demand increases, the weights are lowered, and the motion powers generators to release electricity back into grid. This purely mechanical process doesn't rely on chemical reactions, making it safer, cleaner, and more environmentally sustainable than traditional battery technologies. The science behind gravity batteries is rooted in the concept of gravitational potential energy. When a heavy object is raised, it stores energy based on its height and mass. Once lowered in a controlled manner, this energy is released and transformed into electricity via regenerative motors. Gravitational potential energy does not fade with time, explains Energy Vault, emphasizing why these systems are ideal for long-duration storage. Unlike lithium-ion batteries, which degrade over cycles, gravity systems retain performance over decades, making them both cost-effective and resilient. China is the most active early adopter of gravity battery technology and has several projects underway. The Rudong facility, EVx, is the first commercial utility-scale non-pump hydrogravity storage system in the world, having entered the stage of full-state grid interconnection and hence ready to contribute to national energy needs. As Robert Piccone, CEO of Energy Vault, stated, "I am pleased to see the increased market adoption of Energy Vault gravity energy storage technology in China, adding that it fits in with China's general decarbonization and energy policy ambitions." Gravity storage is now rapidly scaling with 9 ongoing EVx deployments for a total of 3.7 gigawatt-hours across China. Gravity storage mostly finds its success in China due to another major factor. It is adaptable and can coexist with the evolving energy policies of the nation. National laws now mandate that renewable power plant be complemented by storage systems capable of holding back output levels ranging from 20% for 2 to 4 hours. Gravity systems, because of their flexible layout and long-duration capacity, can easily accommodate this function. Andrea Pedretti, CTO of Energy Vault, complimented China's local expertise and manufacturing prowess for the prompt deployment of the EVx and gravity energy storage technology at large, saying, "We have a great partner to rapidly deploy our EVx and broader gravity energy storage technology in China." As the global energy landscape changes, gravity batteries are emerging as a scalable, policy-coherent solution to provide grid stability and reduce dependence on resource-intensive alternatives. But what does this technology look like in action, and how is China already turning this concept into a real-world powerhouse? World's first commercial gravity energy storage system, China's EVx facility is the world's first commercial-scale gravity energy storage system, GSS, marking a significant leap in clean energy innovation. Built through a partnership between Swiss-based company Energy Vault and the Chinese government, this massive structure redefines what a battery can be. Located in Rudong, China, near a large wind farm, the facility is designed to store excess energy when production exceeds demand and release it when electricity needs to spike, ensuring stable grid performance even when renewable sources fluctuate. The EVx system operates by lifting and lowering heavy blocks to convert energy between potential and kinetic states. Each block weighs around 24 tons and is made of locally sourced materials like soil, sand, or recycled construction waste. These blocks are lifted vertically using specialized cranes during periods of energy surplus. When energy is needed, they are lowered to generate electricity, using the same principle that powers pump hydro systems, but without the need for water or specific geography. What actually distinguishes this EVx is its advanced automation and integration with the power grid. The whole structure runs under artificial intelligence and always keeps track of the energy supply and demand status. This smart system independently raises or lowers blocks as betting on grid requirements, thus maximizing efficiency. The site harvested much power, at a peak of 25 megawatts, storing enough energy to supply 100 networks for hours feeding homes during the peaks. It is projected to be over 80% round-trip efficient and last at least 35 years, making the EVx designed for long-term and sustainable operation. In addition, it enjoys a significant economic edge because of its abundant local materials and minimal to no reliance on rare earth elements. The EVx solution appears more stable, scalable, and cost-effective than current lithium-ion megapacks. It is still expensive, environmentally harmful, and quickly loses its effectiveness. China is making strides with this model by putting several hundreds of millions into EVx construction, including one exceptional 2 gigawatt-hour construction project in Inner Mongolia. Gravity batteries versus lithium-ion batteries have been the default choice for energy storage across industries, from smartphones to electric vehicles, thanks to their compact size and high energy density. However, as global energy demand soars with the rise of EVs and AI infrastructure, the limitations are becoming harder to ignore. These batteries degrade over time, pose fire risks, and rely heavily on lithium and rare earth minerals are both environmentally damaging and geopolitically sensitive. As noted in the interesting engineering article, extracting lithium and certain rare earth elements can be environmentally and socially damaging, and China currently controls about 72% of the lithium-ion supply chain, creating added global dependency. Gravity batteries, on the other hand, offer a durable and environmentally friendly alternative that leverages mechanical energy rather than chemical reactions. The concept is simple. Excess electricity lifts heavy weights. Storing energy as gravitational potential. When energy is needed, the weights are lowered to generate electricity. Unlike lithium-ion batteries, gravity systems don't degrade with use, making them ideal for long-duration and repeated applications. Plus, they are made from abundant local materials like sand, soil, and recycled waste, eliminating dependence on costly and scarce mined resources. Gravity batteries also excel for their long-term economics and costs. Their designs and operation give affordableness a different edge compared to traditional storage methods. A strong emphasis on reliability, low maintenance, and smart use of abundantly available materials makes them compelling for scalable energy storage. One prominent project in progress shows the technology can be not only cost-effective but also scalable. Picture larger deployments in the very near term. Suppose lithium-ion batteries maintain their competitive edge on small and short-term application solid asset space and speed of deployment. In contrast, gravity systems would have tall buildings or deep mine shafts for vertical infrastructure, making them unsuitable for most homes or mobile applications. However, they are making strides in grid-scale storage, the scenario where large amounts of renewable energy needed to be stored and dispatched efficiently. Gravity batteries have much to offer because they can produce high-capacity output while avoiding all the environmental and geopolitical problems associated with lithium. They would most likely provide a good complement to, rather than serve as an outright replacement for, lithium-ion batteries, joining with them for a more reliable and diversified worldwide energy strategy. The key to renewable stability, one of the biggest challenges with renewable energy sources like solar and wind, is their inconsistency. What happens when the sun isn't shining or the wind isn't blowing? As the world pivots toward cleaner power, the demand for reliable, scalable energy storage becomes more critical than ever. Gravity energy storage offers a compelling solution by providing a way to store excess energy when generation is high and release it when demand spikes or production drops. This ability to smooth out the highs and lows of renewable energy generation could be the missing link in achieving grid stability worldwide. Gravity batteries operate on a simple yet powerful principle, converting potential energy into electricity by raising and lowering heavy weights. When there's a surplus of power, such as during a sunny or windy day, motors lift massive weights, storing the energy as gravitational potential. Later, when energy is needed, the weights are lowered, and the system converts that stored energy back into electricity using regenerative motors. Unlike chemical batteries, which degrade over time, gravity systems can be cycled repeatedly with minimal efficiency loss, making them ideal for long-duration energy storage. Long service lifetime, low environmental impacts, and flexibility in design are some reasons that make gravity energy storage an attractive option. These systems are not made with rare earths or hazardous chemicals, thus they can be made of locally provided recycled materials like soil, sand, or construction waste. Further, gravity batteries might be incorporated into existing structures or newly custom designed to be built in areas with sufficient vertical height, giving them greater geographical flexibility than traditional pumped hydro storage. With a potential lifespan exceeding 35 years and over 80% efficiency, gravity energy storage is a robust and sustainable means of providing storage. They could now become an integral part of resilient energy infrastructure as increasing renewable adoption proceeds alongside skyrocketing energy demands from EVs and AI. It stabilizes a grid during peak demands, stores energy for long periods, and decreases reliance on fossil fuels and lithium-based batteries, all of which enable it to become a front-runner in any clean energy future. Certainly, this technology may not be suitable for every kind of application, especially at the small or residential scale, but its potential for significance at large scale for refilling the grid makes gravity energy storage a key player in the world for renewables reliability and energy independence. Gravitricity's underground energy revolution. While most gravity battery systems aim to build upward, Gravitricity is flipping the concept, literally, by going underground. This Scotland-based company is pioneering a new form of gravity energy storage by utilizing abandoned mine shafts. Their system, known as Gravistore, is based on the same core principle of lifting and lowering weights to store and release energy. However, instead of constructing tall towers, Gravitricity is repurposing existing vertical infrastructure, like deep mine shafts, to house massive suspended weights that can deliver consistent, clean energy directly into the grid. Gravitricity's first major demonstration took place in 2021 at the Port of Leith in Edinburgh, where a 15-meter-tall test rig was built to validate the system's potential. The setup involved two 25-ton weights suspended on steel cables, controlled by powerful winches. The goal was to test the responsiveness and stability of energy output when the weights were dropped one after the other. After 3 months, the test was deemed a success, proving that underground gravity batteries could be a viable method of storing and delivering energy in real-world conditions. What makes the Gravitricity approach particularly potent is that it can scale and revive mothballed mines. Mines typically extend for several kilometers underground 3 times farther than the tallest structures on Earth. So these vertical spaces allow Gravistore systems to generate a lot more energy. As the same physics applies, energy is defined as mass times gravity times height. The spinal cord of new collaborative projects focuses on achieving much larger and more flexible outputs of power from much more profound and wider shafts, more powerful winches, and larger weights. Systems can give high-energy bursts or more extended periods of release, depending on demand. Päijärvi, Finland, a spectacular project underway in Europe's deepest zinc and copper mine. Päijärvi mine rests at a depth of 1,444 meters. At the present moment, the site is being converted into a huge Gravistore facility, now dominated by inactivity. Päijärvi is being disturbed with the assistance of local development company Päijärvi into a renewal process of both the mine and its surrounding town. By integrating the system with Finland's grid, the power plant will be a robust backup energy provider and widen the opportunities for the inhabitants. Through all such moves, Gravitricity is showing that underground energy storage is the most presumable future of renewable energy. While one company digs deep to unlock the power of gravity, another global giant is scaling the concept sky-high, with ambitions that could reshape the entire energy landscape. China's gravity battery power play. China's bold investment in gravity battery technology signals a potential disruption to the global energy storage industry. While the country already dominates the lithium-ion battery market, controlling around 72% of global production as of 2020, China is now pouring resources into gravity-based energy storage as a long-term, cost-effective alternative. The partnership between the Chinese government and Energy Vault has already led to the construction of the world's first commercial gravity energy storage system, the EVx facility in Rudong, with more projects already in the pipeline. Currently, 6 EVx gravity battery plants are either under construction or in development across China, with capacities ranging from 100 megawatt-hours to 660 megawatt-hours. One of the most ambitious projects is in Inner Mongolia, where plans are underway for a facility capable of handling 2 gigawatt-hours of energy. These initiatives represent over $1 billion in capital expenditure, yet the investment is seen as worthwhile due to lower long-term costs and environmental advantages. The systems rely on locally sourced materials like sand, soil, and construction waste, avoiding the environmental and geopolitical issues associated with lithium and rare earth mineral extraction. Unlike conventional strategies, China's approach goes beyond economic gain. It aims to reshape the very foundation of energy infrastructure. By harnessing domestic resources and focusing on local development, this model supports national resilience and promotes industrial self-sufficiency. Its long-term value lies in the way it integrates cost efficiency, longevity, and design simplicity, 3 factors that many current energy technologies struggle to achieve simultaneously. As a trailblazer, China is now setting precedents that could find resonance across frontiers. Other countries with increasing demand to secure energy storage resources can escape through the cannon hole alternative. Early efforts might soon sprout into global benchmarks, particularly of those who are looking for viable storage with minimum dependence on hard-to-access supply chains. As the development trend continues, this strategy will spark a new era for henceforth catalyzing innovations that will change the way clean energy is stored, distributed, and shared globally. This also fits well into the great story of China as a leading technology country and green improvement within its dual carbon goals, peak emissions by 2030 and carbon neutrality by 2060. Gravity battery innovations are now included in this vision through national pilot programs, such as in Rudong and Zhangye, which were recently declared new energy storage demonstration projects by the National Energy Administration, NEA. These pilot programs not only speed up implementation, but also raise the profile of gravity storage as an essential component of China's clean energy strategy. We're not just building storage, we're building energy independence. One NEA official has been reported to have said at a podium, driving home the point that this technology drives not only national policy but also global leadership. By coupling the development of storage with sustainability and, in the long term, sovereignty, China is not only using gravity batteries as tools of innovation but as an instrumental strategy and influence. The limitations of gravity batteries. While gravity batteries show great promise for large-scale energy storage, they are currently impractical for home use. The main limitation lies in the physics of the system. Storing meaningful amounts of energy requires either very heavy weights, great vertical distance, or both. Unlike lithium-ion batteries that can store high amounts of energy in compact spaces, gravity batteries need tall structures or deep shafts to function effectively. This makes them difficult to integrate into the average home, which lacks the vertical space and structural support necessary to make gravity storage viable. A notable experiment by students at Purdue University demonstrated just how inefficient a residential gravity battery would be. Their prototype used a 2,000-kilogram concrete weight suspended inside a house-sized vertical shaft extending from the basement to the attic. Despite the large weight and full use of the home's height, the total energy stored was equivalent to just 12 AA batteries. Scaling this system to store enough energy for practical household use would require significantly more space, weight, and structural reinforcement, driving up costs and complexity to an unreasonable level for most homeowners. Residential areas require a lot of money to be set up with gravity-based storage systems, and this is another significant disadvantage. Reinforced lift systems, weights, and housing infrastructure would be exorbitantly priced compared with off-the-shelf lithium-ion batteries. Regular maintenance of all mechanical components like pulleys and winches will add a long-term cost burden. Given their affordability and easy availability to homeowners interested in storing excess solar power, lithium-ion batteries continue to be the main choice despite environmental and lifespan concerns. Gravity batteries may not be suitable for individual homes, but a future possibility remains for neighborhood-scale applications. However, deep borehole technologies to support temperature moderation in homes and businesses are already in use for geothermal heating. On the flip side, local gravity battery design could use similar methods by drilling vertical shaft upholds in deep enough to allow insertion or lifting up massive weights. Anyway, until costs and scaling challenges are resolved, gravity batteries will remain in the realms of utility-scale and industrial energy storage. Designing buildings as energy storage systems is a new trend in energy storage and urban architecture. Forward-thinking architects and engineers study the capability of energy-integrated structures, high-rise commercial buildings, often skyscrapers, purposely designed to include gravity storage systems directly into their very structure. This could turn entire city blocks into functioning energy storage hubs in densely populated, vertical cities, where vertical space is more available than open land. As Carlo Ratti once proposed, buildings of the tomorrow won't simply consume power, they'll store and supply it too. However, this fusion of infrastructure and energy storage is still somewhat conceptual in many areas and could help overcome the residential limitations of gravity batteries by scaling them from individual homes to much shared urban assets. The economics of energy storage. When it comes to energy storage solutions, one of the most important metrics is the levelized cost of storage, LCOS. LCOS represents the total cost of building, operating, and maintaining a storage system over its lifetime, divided by the total energy it delivers. It gives a realistic picture of a technology's economic viability, helping utilities and governments decide which systems are most cost-effective in the long run. While upfront costs often grab attention, LCOS reveals the true affordability and sustainability of energy storage options over time. Gravity batteries have emerged as a front-runner in LCOS performance, especially compared to traditional lithium-ion systems. For example, lithium-ion batteries often have an LCOS ranging between $0.25 to $0.35 per kilowatt-hour, largely due to their limited lifespan, chemical degradation, and reliance on expensive rare earth minerals. Pumped hydro storage, a well-established alternative, typically lands around $0.17 per kilowatt-hour. However, gravity battery systems like MWh EVx are projected to deliver energy at less than $0.05 per kilowatt-hour, making them one of the most cost-efficient storage solutions currently in development. Several reasons lead to the low LCOS of gravity batteries. One thing is that the materials used, namely sand, earth, or recycled waste, can be easily obtained and are very inexpensive. Another aspect is the operational lifetimes of gravity batteries, which would last for 35 years or more without considerable degradation. Furthermore, they are not too demanding on maintenance while not requiring any costly raw materials such as lithium, cobalt, or nickel. Lastly, high efficiency projected at greater than 80% means very little energy will be lost in the process of storage and release, thereby improving cost-effectiveness with time. In the face of surging energy demand and deepening dependence on renewables, this is a time when LCOS is to be preferred more than ever. Low LCOS technologies stabilize the grid at lower costs and keep fossil fuel use to a minimum, thus allowing consistent power delivery when wind or solar generation dips. As the AI infrastructure, EV adoption, and decentralized energy production take off worldwide, long-duration storage will be increasingly important in this low-cost segment. This puts gravity batteries in contention in the LCOS area, where they possess a great ability to maneuver through the economics of energy storage in the future. LCOS is more than just numbers. It also points out the different strategic advantages that come in deeper aspects of national energy policy and resource independence. Countries that aim at mitigating the heavy reliance of foreign supply chains, especially in critical minerals like lithium and cobalt, are now beginning to assess technologies such as gravity batteries partly based on the cost but increasingly on the resilience aspect. Energy security is no longer just about oil, it's about access to stable, affordable storage, observes Dr. Juliet Davenport, energy economist and founder of Good Energy. For instance, the collaboration between Switzerland and Energy Vault shows how nations rich in engineering expertise but poor in mineral resources can catapult themselves by investing in infrastructure-based storage solutions. Similarly, China's deployment of gravity systems is in line with a broader agenda of localizing both manufacturing and energy systems, and, thus, reducing vulnerability to trade disruptions. In this sense, then, LCOS is not just a monetary metric. It becomes an eye-grow-town to viewing energy sovereignty, sustainability, and long-term national resilience. Turning old mines into energy gold mines as the world searches for sustainable energy storage solutions, old, abandoned mine shafts are being reimagined as powerful tools in the energy transition. Gravitricity, a Scotland-based energy startup, is leading this innovative approach with its Gravistore technology, which transforms decommissioned mines into gravity-based energy storage systems. By suspending massive weights inside deep vertical shafts, gravitricity can store and release energy by simply raising and lowering these weights. This concept utilizes the same physics as other gravity batteries, converting potential energy into electricity, but leverage existing infrastructure to reduce construction costs and environmental impact. One of the major benefits of using old mines is their extreme depth, which allows for much greater energy storage capacity. The deeper the shaft, the more energy that can be stored, because the energy output is determined by the mass of the weight, gravitational force, and the height it travels. While the tallest buildings in the world, like the Burj Khalifa, stand around 828 meters, mines can reach depths of over 3,000 meters, offering significantly more vertical space for energy storage. This allows gravitricity to deploy larger weights and stronger winches to deliver both high power output and longer duration energy release. Repurposing mine shafts for energy storage not only avoids the prohibitive costs of decommissioning, but also makes such a decommissioning look very environmentally damaging when compared to building new storage sites. Decommissioning mines is costly, lengthy, and often hazardous. Turning them into clean energy storage sites allows entities such as gravitricity to extend their utility for a further 50 years. The innovative repurposing of existing structures helps meet renewable energy targets, mitigates environmental unrest, and supports a circular economy regarding infrastructure, all while balancing out the growing demands on national power grids. It involved the transformation of inactive industrial infrastructure into green energy assets. This trend is part of a wider cultural shift towards sustainability and circular economy. Projects such as these are gaining traction throughout Europe and beyond, as governments try to achieve their climate goals without the imprint of new construction. According to the International Energy Agency, IEA, Energy storage capacity globally must expand 15 times by 2040 to support net zero targets, an ambitious leap that demands an adequate measure of ingenuity and resourcefulness. As Julian Leslie of the UK's National Grid ESO has said, we need to think creatively about the assets that we already have. Gravitricity's model does just that. It articulates trend toward brownfield redevelopments where old industrial sites are optimally reused rather than neglected. By reusing mine shafts, communities not only adopt cleaner sources of energy but also actively protect local heritage and put new life into long-forgotten monuments, thereby transforming energy transition stories into regeneration stories, not mere replacements. Reviving abandoned mines may be genius, but can gravity batteries keep up with tomorrow's energy race? Can gravity batteries scale in time? As the global shift toward renewable energy accelerates, the need for large-scale, reliable energy storage has become urgent, and gravity batteries may be one of the most promising solutions. These systems offer long-term durability, minimal degradation, and low environmental impact, making them attractive alternatives to lithium-ion batteries. However, the big question remains: can gravity batteries be built and deployed quickly enough to keep pace with the rising demand driven by electric vehicles, AI infrastructure, and solar and wind power expansion? One of the main challenges to scaling gravity batteries is the time and capital required to construct them. Unlike lithium-ion systems, which can be quickly installed in modular units, gravity batteries rely on tall custom-built towers or deep mine shafts. These projects require heavy-duty construction, large volumes of materials, and sophisticated automation systems. Even though materials like sand and recycled waste are inexpensive and widely available, the infrastructure itself takes months or even years to complete, potentially slowing down deployment on a global scale. This shows that, with sufficient funding, gravity battery installations can be rolled out on a mass scale, as countries such as China are rapidly pursuing this area. China has also completed the world's first commercial gravity energy storage system, namely the EVx in Rudong, with at least 6 more installations in the pipeline. One in Inner Mongolia is expected to generate a staggering 2 gigawatt-hours of energy. Together, these facilities represent a capital expenditure of over $1 billion, demonstrating that gravity batteries can scale, at least on a national level, with political willpower and funding. Gravity batteries might not be viewed as a magic solution. They are a key piece to a larger puzzle. They might not realistically replace lithium-ion or any other battery technology due to long construction timelines and vertical land use, particularly in short-term or mobile applications. Instead, they find their way into stable, long-duration energy storage for grid-level applications, balancing intermittent renewables with power supply during peak demand. Should development continue as anticipated, gravity batteries will prove to be a cornerstone of the global clean energy infrastructure. Time, however, will tell if they will scale with the pace demanded by the world's fast-growing needs. While the government is sponsoring national projects, there is growing private sector involvement even beyond that, as it begins to influence how gravity storage will look like globally in the future. A case in point is Gravitricity and other companies looking for ways for faster modular deployments across the board. Repurpose existing mine shafts from London to Europe, cutting construction time and pre-installation expenses significantly. As novel ways of doing things merge with old infrastructure, this hybrid model could prove indispensable for scaling up in areas that do not have the budget or geography for hefty new builds. Gravitricity Managing Director Charlie Blair said, "We have a reliable storage solution waiting for those years to build towers by using what's already beneath our feet." Besides that, it would go much further because cultural change is already in the air concerning circular economy resource reuse, reducing waste, and faster project timelines with smart localized solutions. Localized smart solutions may achieve storage in the ground and smart thinking with gravity. Because on soaring demand for energy, global storage may not move only up but down also. Thanks for watching. If you found this interesting, give it a like, drop your thoughts in the comments, and don't forget to subscribe for more stories just like this. Want to see what's next? Click the video on your screen now. You don't want to miss it.